Welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is Luca Zamboni from the University of Lyon, and he is going to talk to us today about singular words.
Okay, thank you very much, Narad, and thank you very much for the invitation. So this is joint work with Alessandro De Luca and Marcia Edson. And I would also be remiss if I did not mention two other people. One is Gerhard Ramharter, and the other is Sebastian Ferenczi, with both of which I've had several very insightful exchanges. So let me start with a warm-up exercise, and I think it'll become clear why I'm doing this in a few moments. So I'm going to start with reminding you what is a Lyndon word. So in order to define Lyndon words, you need for your alphabet to be linearly ordered. So I'm only going to be taking examples from a binary alphabet, so A less than B. So a finite word X is Lyndon if and only if X is smaller than each of its suffixes. So here's a couple of examples of Lyndon words. So now what you can do is you can take the complete opposite property, so not the negation of this, but the complete opposite property, and say a word is anti-Lyndon if it's strictly bigger than each of its suffixes. So I don't want to associate names to these notions. I'm just sort of inventing them. It's not going to be important. So here's a couple of examples of anti-Lyndon words. You can see I got them from the previous examples by just changing the A's and the B's. And in fact, at first glance, one might think that there's nothing, interesting going on, in the sense that if you just change the order of your alphabet, then if you're Lyndon with respect to one order, you'll be anti-Lyndon with respect to the other order. But there's a little bit more going on. For example, we know that Lyndon words are always primitive, which is not the case for anti-Lyndon. So for example, AA is anti-Lyndon. We also know that if I have a primitive word X, then amongst all its cyclic conjugates, there's exactly one, which is Lyndon. And this also is not true for anti-Lyndon. So here's two anti-Lyndon words, which are cyclic conjugates of one another. And now two other variants on this notion is to change the order. So if instead of taking the usual lexicographic order, you take the alternating lexicographic order, then you can define the notion of alt-Lyndon by saying that a word is alt-Lyndon if it's less than each of its proper prefixes relative to the alternating order. So here's a couple of examples. So you might notice that AB here is actually smaller than AA with respect to the alternating order, and ABA is less than ABB with respect to the alternating order. And again, even for this one, you can take the opposite notion. So you say a word is anti-alt-Lyndon if it's greater than or equal to each of its prefixes relative to the alternating order. And here's some examples. Okay, so this warm-up exercise has two purposes. One is to just review the notion of the usual lexicographic order and the alternating lexicographic order, both of which will come up in the sequel. And the other reason is because, so here's the outline of the talk. I'm going to start by talking of some extremal properties in the theory of finite continued fractions. So there's actually going to be two different kinds of continued fractions we're going to consider, what are called the regular continued fractions and semi-regular continued fractions. And for each one, we're interested in the max and the min. So if you think about it, that's four different problems, two continued fractions, and each one max and min. And it turns out that the solutions to these extremal problems are characterized by some special combinatorial properties, which are all sort of variations of one another, just like we see in this example here. And so we're going to be interested in these four properties. And then what we'll see is that one of the four behaves very differently than the other three. This is not exactly clear to me why this is, but it is what it is. There's one that's certainly more elusive than the other three. And of course, that's the one we're going to be interested in. And we're going to call that the singular property. So singular words will be words that satisfy the singular property. And so we're going to study this singular property, and we're going to see that it's fundamental in at least 3 different areas. One is, well, this in the context of these extremal problems that I will be talking about. Another example of the singular property is it turns out that it's identical to the Markoff property in the context of bi-infinite binary words. And the third context in which it appears, which is somewhat surprising because it's not number theoretic in nature, it has to do with codings of symmetric interval exchange transformations. Of course, there's number theory there too, but that's not where it appears. It appears in the structure of the orbits of points. So sort of, if you wanted the language associated to symmetric interval exchange transformations. And so anyway, what we do is we develop an algorithm for constructing all finite singular words. So because they represent these extremal solutions to these problems. And our algorithm is somewhat reminiscent of the one for constructing Christoffel words, in the sense that there's an Euclidean kind of algorithm. There's an arithmetic algorithm that you run, and then you feed the output to a combinatorial algorithm, which works in parallel. And in the case of Christoffel words, the combinatorial algorithm is morphic, or you can do it using iterated palindromic closures. In our case, it won't be either one. And but in fact, I won't talk about the combinatorial algorithm, but I will talk about the Euclidean algorithm, and it'll turn out to be a non-commutative variant of the usual Euclidean algorithm. Okay, so let me start by introducing some of the main actors involved. So there's the regular continuant, which I'm sure you're all familiar with. So I will denote it by K. I won't be putting, commas here. I'm going to be thinking of these as just words made up of positive integers. It's just easier not to put the commas and the parentheses. And it's defined recursively according to this rule. One key property is that it's invariant under reversal. So here X starts represents the reverse of a word. So K is constant if you reverse the word. And as you all know, it corresponds to the denominator of the terminating regular continued fraction x1 through xn, with partial quotients x1 through xn. Of course, the numerator also is a continuant. So maybe a little less known is the semi-regular continuant. I will denote it by k dot and often refer to it as by k dot. It's defined recursively in much the same way as the regular continuant, except there's a minus there. Okay, so that's the main difference, but it's also invariant under reversal. And you want to stay away from the number 1. So you need the xi's to be at least 2, otherwise you could possibly be getting, negative numbers or dividing by 0 or something like that. So when I talk about the k dot, the semi-regular continuant, I will always assume that the numbers are greater than or equal to 2. Another way of comparing them is you can form this matrix. And so K is just the permanent of this matrix, and K dot is the determinant of this matrix. So it takes parity into consideration. And last but not least are the cyclic analogs of the 2 continuants I just mentioned. So I will be denoting those with this little circle thing here. So these are actually defined on circular words or cyclic words. And they were first introduced by Motzkin-Straus in the mid-50s. And so here are their definitions. And you can just check that if you replace x1 through xn by any cyclic conjugate of x1 through xn, the right-hand side is constant. So these are defined on cyclic words. And some of you might have also seen this first one, the circular version of K, in a 2008 paper by Jean Berstel and Boisson and Cartan. They called it circular continuant, and it was introduced or is considered in connection with Hopcroft's automaton minimization algorithm. Okay, so let me explain the extremal problems that we're going to be interested in. So suppose I give you a word X made up of k distinct positive integers, sort of ordered A1 through AK, with their multiplicities N1 through NK. And of all permutations of the word X, I'm interested in the ones that give me the maximum and the minimum value of K. So of all possible ways of rewriting the word X, up to permutations, can you describe one that gives me the maximum for K and one that gives me the minimum for K, for the regular continuant, okay? So there's no suggestion here that this should be unique. In fact, we know that if you have a extremal arrangement and you take its reverse, then that's also extremal because K is invariant under reversal of a word. So there may be at least two, but the function K is very far from being injective. So there's a priori no reason that there can't be many more. But just the problem was to describe one, and this problem seems to be attributed to Nickel from the mid-50s. So you can consider the same problem with regards to the semi-regular continuant K dot. And in 1983, Ramharter posed the same question for the cyclic continuants, okay? So in the linear case, so linear, I mean linear words, not cyclic words, there are two continuants, and in each case you want the max and the min. So that's 4 different problems, which is reminiscent of that warm-up exercise. 4 variations of sort of the same thing. And also in the cyclic world, if you're dealing with circular words, then also there are 2 continuants, and in each case you want the max and the min. So there's also 4 things going on there. Okay, so there were some partial results to this question starting in the mid-50s, already with Motzkin-Straus, and then I think in the 70s, Kusik gave some partial solutions to this problem. But the problem was largely settled in the mid-80s by Ramharter. So what he found both the maximizing and minimizing arrangements for the regular continuant K. At the same time, he also found the minimizing arrangement for the semi-regular continuant. In all 3 cases, he showed that the extremal arrangements are unique up to reversal. That is, the only redundancy is the reverse. There's no other combination that can achieve the max or the min, and independent of the actual values of the positive integers A1 through AK. In other words, it doesn't use the ring structure at all of Z. There's no rule that says, well, if twice A1 plus A2 is bigger than A3. No, it just depends on the relative order of the numbers A1 through AK and not their actual values. So let me illustrate this with an example. So say I have my word X here like before. So here's the formula for the maximizing arrangement. So what do? You take the largest positive integer AK and you put it here. And if you have any leftover AKs, meaning if NK is bigger than 1, then you put it here at the end. Then starting from the right-hand side, you put the next largest integer here, and the leftovers go here. Then you go here and you put the next largest integer, the leftovers go here, and you continue in this way. So I just worked out a simple example. The word consisting of 2, 3, 5s, and 8. You put your first 8 here, leftover 8s go there. Next largest integer is a 5, you put it here, leftover 5s go here. Then you put your 3, leftover 3s, and the 2s get crammed in the middle. Okay. So on the other hand, the determination of the maximizing arrangement for K dot turned out to be more difficult. Remember, he found the extremal arrangement for K and the minimizing arrangement for K dot, but he got a little bit stuck on the maximizing arrangement for K dot. So let me cite some passages from his paper. He notices that there is an infinity of essentially different patterns. So he's referring to the maximizing arrangement for K dot. The maximizing arrangements have to be described in terms of an algorithmic procedure, as their combinatorial structure is exceptionally complicated. However, he did, in that same paper, manage to solve the problem for the binary case. So if you have a word just consisting of 2 distinct positive integers, A1 and A2, then he showed that the maximizing arrangement for K dot is unique always up to reversal, and independent of the actual choice of the positive integers A1 and A2. Okay, so now fast forward 20 years, and Ramharter writes 2 more papers on the subject, one of which is entitled Maximal Continuants and the Fine-Wilf Theorem. So what happens there? So he shows that on the binary alphabet, the maximizing arrangement for k dot is a finite Sturmian word. And he develops a Euclidean-like algorithm for constructing these arrangements as a function of the Peric vector n1 and 2, the number of A1s and the number of A2s. He also shows that the palindromic binary maximizing arrangements, always for k dot, are in one-to-one correspondence with the extremal cases of the Feynman-Wilf theorem with coprime periods p and q. Now, I'm not suggesting that they're always palindromes. I mean, in particular, if n1 and n2 are both odd, it'd be a little tricky to construct a palindrome having odd number A1s and odd number A2s. But if it should be a palindrome, then it's closely related to the extremal words in the Feynman-Wilf theorem. In fact, what we will see is they are basically central words padded on either side with the letter A. And in that same paper, he conjectured that in general, the maximizing arrangement for k dot should be unique and independent of the actual values of the positive integers ai. And if I'm not mistaken, he also verified this conjecture in case all the ni's were equal to 1. In other words, if each ai occurs just once in the word, then he was able to describe the maximizing arrangement and showed that it's unique up to reversal and independent of the actual values of the positive integers. Okay, so let me explain what is the central idea that was developed by Ramharter in these paper, in that 1983 paper. So suppose that we start with a word x consisting of positive integers, and now factor x, decompose it into 3 parts, u star vw. Remember, u star is u backwards, is the reverse of u. V and w, where what you want is that v is not a palindrome and u is different from w. Okay, so now the entries, I mean, the letters in X are positive integers, so they're naturally ordered by the order on Z. Okay, so because V is not equal to V star and U is not equal to W, we could consider comparing them lexicographically. So we know that V will either be less than V star or bigger than V star, and the same is true between U and W. U is either less than W or bigger than W. So suppose that the inequalities go this way. In other words, U does what V does. If V is less than V star, U will be less than W. Or conversely, if V is bigger than V star, then U is bigger than W. Okay, so just sort of remember it that U follows V. Well, then in that case, what he showed is that if you reverse the V in X, so you'll get a different word because remember, V is different from V star, okay, then K dot actually increases, okay? Now, warning, in order for this theorem to be true, you have to adopt the opposite convention of the true dictionary order with regards to proper prefixes. In other words, if W is a proper prefix of U, then W is bigger than U. So in particular, the empty word counts for infinity. So one way of sort of remembering this or keeping it straight, because it's also going to apply for the alternating order, which I'll mention in a moment, is, so of course, this is not an issue between V and V star because they have the same lengths, but it could be an issue with U and W. So if U and W are of different lengths, just add a bunch of infinities to the shorter of the two until they have the same lengths, and then just compare them lexicographically in the usual way, where you adopt the convention that infinity is bigger than any other letter. Okay, so that's, just remember it that way. If U is shorter than W, just tack on a bunch of infinities to U and then compare U and W, and they'll have the same length. Okay, so so what this means, I mean, what this theorem is saying is that if you have a maximizing arrangement for K dot, then you should not be able to factor X in this form where the inequalities go this way. Because if you could, by reversing the V, you would get something bigger, which means that this wasn't maximum, okay? And conversely, the minimizing arrangement should have the property that each factorization of this kind the inequalities have to go this way, okay? So this is a little bit like what we were saying before, Lyndon and anti-Lyndon. A typical word, normal run-of-the-mill word, when you factor it in this way, some factorizations, the inequality will go this way, and for other factorizations, they'll go in the opposite way. For the maximizing arrangement, we want them all to go in the other direction. We don't want any of this. And for the minimizing arrangements, they should all go in this direction. Okay, and there's a similar theorem that he shows that works exactly the same way, except that the usual lexicographic order is replaced with the alternating lexicographic order. But otherwise, the direction of the inequalities doesn't change. And the other thing is it tells you something about K, not K dot. And it tells you that if you reverse the V, then this time K dot decreases. So here it increases, here it decreases. So this means that if you want a minimizing arrangement for K, then you should not be able to satisfy the conditions of this theorem. And conversely, the maximizing arrangement, every factorization would satisfy the conditions of this theorem. The other sort of interesting thing to note is that if you sort of think about it, K is more similar to the usual Lex order. Neither one takes the parity into consideration, whereas K dot, remember, was a determinant, and the alternating lexicographic order, of course, takes parity into consideration. So these two are sort of similar to each other, and K is sort of similar to this. But as often happens in life, you know, opposites attract one another. And so they actually, in this theorem, they get paired up in this way. And what one might expect is that they sort of compensate one another. In other words, that the behavior of this pair and the behavior of this pair will sort of be the same because they were opposites and they paired up in this way. But in fact, we'll see that that's not at all true. They'll actually behave quite differently. Okay. So let me illustrate theorem 1 with an example. So this is just the same theorem I had up a second ago. So here I took a random word X consisting of 2s, 3s, 4s, and 5s. So it has 3 many 2s, 6 many 3s, etc. And we're going to look for, within X, factorizations that verify the condition of this theorem. So here's one. The red is the V. So this is V. W is 2, 3, 5, and you have to read it backwards. So U is 2, 3, 3, 4, 5, 5. Okay. So we notice that V is smaller than V star. V begins in a 4 and ends in a 5. And we also notice that U is less than W because U begins in 2, 3, 3, while W begins in 2, 3, 5. So we're exactly in this situation here. V is less than V star and U is less than W. So Ramharter's theorem tells us, well, if we reverse the V, we reverse the order of this word, then K dot should actually increase. So let's do that. And in fact, we see that it does increase. Trust my calculation. So here I just reversed the V part, kept everything else the same, and K dot increases. Okay. So now let me call this new word X prime. And let's see if within X prime we have other factorizations that satisfy this condition. Well, here's one. So again, V is the red part, 4, 2, 3, 5. U is this whole long thing read backwards. And W is the empty word, okay? So here, V is again less than V star, because V begins in 4, ends in 5. And U is less than W, because remember, W is the empty word, so it counts for infinity. Okay, so again, we're back in this situation here. And Ramharter's theorem would tell us, well, if we reverse the 4, 2, 3, 5, then K dot should increase. And indeed it does. Okay, so we can iterate this process and let's imagine what happens as we iterate this process. Well, the fact that each time we're reversing V, we're not changing the abelian class. I mean, all these words, they still have the same number of 2s, 3s, and 4s and everything. So we stay within the same abelian class, which is, of course, finite. Okay. And unless we make a mistake, we're never going to cycle back to something we've already seen. Why is that? Because every time we reverse the V in X, the continuant, K dot, actually increases. So we can't possibly get the same word twice, because we have this valuation that's sort of saying that every time we do this process and we apply K dot to the resulting word, it's actually increasing. So if we keep iterating this process, we will eventually come across a word that has no factorization that verifies this condition, okay? In other words, we will have found a maximizing arrangement. And so here's the word that you would find. This the one denoted X max, okay? And here's its K dot value. As you can see, it's bigger than all the other ones we've encountered. And just so that you can see, I also wrote down what the minimizing arrangement is. And here's its K value. And you can already pretty much see the difference. Look at how regular this word is compared to this one. And this is exactly what sort of Ramharter ran up against, is he was able to sort of understand these words, but these words he wasn't quite sure how to build them just from this parent vector. So, okay, and the other thing I wanted to mention in this example is, so let's fix again this abelian class. So we're looking at all words consisting of 2, 3, 4, and 5 that have this, with this multiplicity, this parent vector. So starting from this word X, we took a factorization of X that satisfied this condition of the theorem, and we reversed the V, and we got this new word, X prime. But imagine us doing this for every possible factorization of X which verifies this condition. So take a word X in this abelian class, like this one, and for each factorization of X which verifies the condition of theorem 1, reverse the V and put a directed arrow from X to X prime, okay? So if you do that, you can endow the abelian class of this word with the structure of a directed graph. And the fact that every time you have a directed edge from X to X prime, you know that K dot of X prime will be strictly bigger than K dot of X, tells you that in this directed graph, you cannot have cycles, okay? So we can, using this theorem, we could endow the abelian class of this word with the structure of a directed graph, and this directed graph will not have cycles. And of course, the words we're interested in are exactly the vertices that have out degree 0, which would be this one, for example. And on the opposite side, you have the vertices that have in degree 0, which is, for example, this one. So this is all I want to say in this next slide, is that you can do this more generally, even if the xi's are not made up of positive integers. If you have an ordered abstract alphabet, you take a word X, you look at its abelian class, so all permutations of X. You take two words Y and Z in the abelian class of X. You put a directed edge from Y to Z whenever Y looks like U star VW, and Z is obtained from Y by reversing the V. So Z looks like U star V star W. And the inequalities between V and V star and U and W are the same. So V is less than V star, then U is less than W, or V is bigger than V star, U is bigger than W. So each abelian class can be given the structure of a directed graph. This construction is easy to see that factors to the quotient. So this is an abelian class where you identify a word in its reverse. In other words, if you have a directed edge from Y to Z, there would be one between Y star and Z star. And so what Ramharter proved is that in this directed graph, which I'm going to call G dot of X, so first of all, it's acyclic, and that's because we have those valuations that tell you that if you have a directed edge from Y to Z, then K dot of Z is strictly bigger than K dot of Y. So you can't possibly form cycles. And this graph has a unique vertex within degree 0, which corresponds to the minimizing arrangement of K dot. And hence, in particular, this graph is connected. So, and it's from this theorem that he's able to conclude that the minimizing arrangement of K dot is unique because it corresponds to that vertex. Well, unique up to reversal, but here we are identifying words in its reverse. So it corresponds to the unique vertex within degree 0. Okay. Now you can do this exact same construction with theorem 2. That's the one where you have the alternating order. Okay. So again, you take the abelian class of some word, and given two words Y and Z, you put a directed edge from Y to Z. If Y, you can factor it this way, Z is obtained from Y by reversing the V. And this time, the inequalities that you want to be satisfied are relative to the alternating lexicographic order. And once again, this construction factors to the quotient. And this time the graph is a little bit more regular than the previous one. He's able to show that it's acyclic, and this time there's a unique vertex within degree 0 and a unique vertex without degree 0. Okay, so before we don't know about the out degrees, but here we have unique in degree and unique out degree. And so it's from this that he's able to conclude that both extremal arrangements for the regular continuant are unique up to reversal. So this next slide is not very important, but I just wanted to mention that in this paper of Dolce, Restivo, and Reutenauer, they have this way of associating to every infinite 0-1 word a family of lexicographic-like orders on a star. So I'm not going to write out the actual definition, but basically, if you have two words, again, tack on a bunch of infinities to the shorter one until it has the same length as the longer one, and then look at the first time they deviate. Look at the first position where the two words deviate. So say that's in position J. So then look at the J's coordinate of the word alpha. If it's 0, then use the usual order to compare the two words. And if it's 1, then you take the opposite order. So from this point of view, the usual lexicographic order would correspond to the infinite word 0 to the omega, and the alternating order would correspond to the infinite word 0, 1, 0, 1, 0, 1, etc. Okay. So once again, you can do this directed graph construction. So you take some abelian class, and given two words y and z, you put in directed edge from y to z if the usual thing, except this time you're using these exotic lexicographic orders, okay? And also this factors to the quotient. The only thing here is you don't have the valuations. You don't have the k and the k dot that tell you that you can't get cycles. So the question is, can you get cycles or not? Well, what we show is that in general, you will get cycles. So if you do this construction for some word alpha, then these directed graphs are acyclic for each x if and only if either alpha is 0 to the omega, which means you are using the usual lex order, or alpha is 0, 1, 0, 1, in which case you are using the alternating lexicographic order. Okay, so there's no other hidden continuants that would work well with this construction with respect to these more exotic orders. Okay, now just a brief digression to the cyclic world. Okay, so we were able to prove analogs of theorem 1 and theorem 2 that I mentioned earlier for cyclic words. This is a little bit simpler because you just consider factoring a cyclic word into two pieces, uv, there's no w. Okay, so you consider all factorizations of x as u times v where neither u nor v are palindromes. So again, you can compare u and u star, v and v star. And if the inequalities are opposite, so in other words, u is less than u star, but v is bigger than v star, or u is bigger than u star and v is less than v star, then reversing the u actually increases the cyclic semi-regular continuant. Okay, so this gives you a valuation to work with in abelian classes of cyclic words. And there's a similar theorem for the regular cyclic continuant. It works just like this one, except there's the alternating order involved. Okay, so you can do those graph-directed constructions for cyclic words, just like we did several times already. And so here the theorem that you get is that in the directed graph where you use the alternating lex order, then there's a unique vertex within degree 0 and a unique vertex without degree 0. Same thing we saw in the linear case. And so in particular, the extremal arrangements for the circular version of K are unique up to reversal and independent of the values of the AI. In contrast, if you use the regular lexicographic order, okay, and you get this directed graph, then all you can say is that it has a unique vertex within degree 0, but there may be many without degree 0. And so in particular, what you can say is that the minimizing arrangement for the cyclic version of the singular continuant is unique up to reversal and independent of the values of the AI. Okay, so I hope I've convinced you that these four properties which seem very similar to one another, this sort of chain of inequalities where you either want them to go one way or in the opposite way. And with respect to the usual Lex order or the alternating Lex order, they seem sort of similar to one another, but there's one that behaves differently, which is the one that corresponds to the out degree 0 here. It's the maximizing arrangement for the k dots. So that's the property we're going to be interested in, and so that motivates the definition of this definition. So so A is an ordered alphabet. X could be a finite word, one-sided infinite word, two-sided infinite word. So we say X is singular if for all factorizations, X equals U star VW, the only thing that we insist is that V is finite, and U and W are what they have to be. I mean, if X is finite, then U and W are both finite. If X is one-sided infinite, U will be finite, W will be one-sided infinite, etc. They are what they are. But for each factorization like this with V finite, and V not equal to V star and U not equal to W, what you want is that V is less than V star if and only if W is less than U. So W should have the same inequality with U that V has with respect to V star. Okay, so it's easy to see that if X is singular, so is its reverse. This is also true if I took a one-sided infinite word, but then if I reverse it, I get sort of a one-sided in the wrong direction. Okay. And the definition for cyclic is even simpler. So you take a cyclic word W and you say singular if every time you factor it as U times V, with U and V non-palindromes, then the inequality between U and U star and V star should be the same. Okay. So also here in the cyclic case, if X is singular, so is its reverse. Of course, the reverse just means you change the orientation on the circle. And there's a connection between linear singular words and cyclic singular words, and it's given by the following. If X is a finite singular word, a linear singular word, then if you sort of take a, I guess a 1-point compactification of X, you add the symbol infinity, which is bigger than every other letter, and you close it up to make a circle, then this should be, then this is cyclic singular. So this tells us that if we have a recipe, if we have a way of constructing all cyclic singular words with a certain Perec vector, then we know how to construct all linear singular words for any given Perec vector. Because, for example, if I want to construct a linear singular word with, say, with Perec vector 237, then I just add a 1 at the end of that Perec vector. So I consider 2371, the 1 corresponds to the infinity. And I construct the cyclic singular words having Perec vector 2371, and then I just open them up by removing the symbol infinity, and I get all the possible singular words, the flat ones, the linear ones. Okay. So let's start with an analysis of the binary case, because it's really the simplest. So a bi-infinite singular word in the binary case is just balanced. It's equivalent to being balanced. And this is actually very simple to show. For one-sided infinite words, if you take them to be aperiodic, then singular is equivalent to being Lyndon and Sturmian. The Lyndon comes up because of the issue with the lexicographic order relative to proper prefixes, which is not an issue here because these are bi-infinite words. Cyclic. A cyclic binary word is singular if and only if it's the power of a Christoffel word. Okay. So you might remember in Reutenauer's talk, he gave a arithmetic characterization of Christoffel words using the regular continuant. Here's another one. Christoffel words are those words which maximize the cyclic version of the semi-regular continuant. And finally, for finite linear words, X is singular, so these are again binary. X is singular if and only if either X or its reverse is of the form b to the n, so that means of course there's no a's in X, or X looks like a b to the n or its reverse, b to the n a, or if there's at least 2 a's in X, then X looks like AVA, where V is a bispecial Sturmian word. Okay, so in particular, if you take V to be a central word, so those are bispecial within an infinite Sturmian word, then words of this kind are what the when called singular Sturmian words. Okay. So you can see that so let me remind you also of a result of Gabriele Fischi that said that V is a bispecial Sturmian word if and only if A prime V B prime or A prime B prime are distinct is a power of a Christoffel word. So this, you see, they're very close, right? It's the only difference is this last A is it has to be changed to a B, and then it becomes a Christoffel word. So this allows us to easily build singular words starting from any Perec vector in the binary case, because we know how to build Christoffel words. There's lots of known algorithms for doing that. So let me do an exercise. Suppose we want to build a singular word with Perec vector 714. So we want 7 many A's and 14 many B's. So the first thing is we'll build a Christoffel word with Perec vector 615. Why 615? Because at the very end, the last B is going to become an A. So that will give us the 714. Okay. So how do you build a Christoffel word with 615? Well, you first see that 3 is the GCD. So you really have to build the primitive Christoffel word based on 2,5, and then you would cube it. So I'll just tell you what that primitive Christoffel word is. There's many known algorithms for doing this. Okay, so here's the Christoffel word with 2 A's and 5 B's. You cube it. So now you're up to here. You've got your Christoffel word or power of a Christoffel word corresponding to 615. And the very last B, you change it to an A. And so here is the answer in the back of the book, the singular word with Perec vector 714. Okay. So let's go back to the bi-infinite binary case. Okay, so let's take ordered alphabet, AB, A less than B, and X is a bi-infinite word. So let me remind you what the Markoff property states. It says that for all factorizations of X in the form U star A prime B prime W, with A prime not equal to B prime, and U not equal to W, A prime is less than B prime if and only if W is less than U. Now, when Markoff first wrote this property down, he didn't assume that the alphabet was ordered, but it's completely equivalent to this. Even if you take the opposite order, it would work exactly the same way. So this is the singular property where the length of V is 2. The V is this part here, right? So we're saying that that V is less than V star, if and only if W is less than U. Okay, so the Markoff property can be seen as a special case of the singular property where the length of V is equal to 2. So in 2006, Reutenauer proved that the Markoff property is equivalent to the balance property. Well, we just saw that the singular property is equivalent to the balance property for binary words. So if you put these two results together, you get that the singular property in the framework of bi-infinite binary words is completely equivalent to the Markoff property. Now, you could actually prove this directly using sort of Sturmian morphisms. You don't have to go through the balance thing. But anyway, it shows that the singular property is the same as the Markoff property in the case of bi-infinite binary words. So we'd like to sort of generalize this to higher alphabets, always in the context of bi-infinite words, but not just binary. So for that, I need to sort of remind you about interval exchanges. So I'm not going to write a technical definition of an interval exchange, but basically you take the interval 0, 1, chop it up into finitely many pieces, many subintervals, which you then rearrange according to some different order. So here, this is an example of a 4-interval exchange. It's what's called a symmetric 4-interval exchange in the sense that the 4th interval becomes the 1st, the 3rd becomes the 2nd becomes the 3rd, and the 1st becomes the 4th, okay? And often when people study interval exchange transformations, they insist on this condition, this property called IDOC, which was introduced by Keen. And the IDOC condition says that the k-1 negative trajectories of the gamma i's, so the gamma i's are the points of discontinuity of the interval exchange, these sets should be infinite and disjoint. So the I here is for the infinite, the D is for disjoint. It's the infinite disjoint orbit condition, okay? So you don't want, for example, gamma 1 when you take its negative trajectory to end up back on gamma 1, nor do you want gamma 1 to end up at gamma 3 or something like that. Okay, these sets need to be infinite and they need to be disjoint. So let me introduce, so we have the alphabet 1 through K. So in 2008 with Sebastian Ferenczi, we gave an axiomatic characterization of languages defined by K-interval exchange transformations satisfying the IDOC property. Okay, so, and the characterization that we gave involved 2 linear orders on this alphabet. So where do these 2 linear orders come from? Well, you have, remember, the original K intervals. There's no reason you have to label them 1 through K. You can call the first interval 7, the second interval 3, whatever. And then you have their rearrangements. Okay, so the labeling of the initial intervals gives you the order delta less than 1, and the order of their images gives you the order delta less than 2. Okay, so we had a series of conditions. A lot of them were actually addressing the IDOC property, but the fundamental property, I mean, the one that really, if you remove all the buzzwords and everything else, minimality, everything else, the one that really counts, the one that's really important is what we call the order condition. And it says that for every word W, if AWD and BWC are in your language, with A different from B and C different from D, then A is less than B relative to the first order, if and only if D is less than C relative to the second order, okay? So in particular, if you take the first order to be the usual order, 1 is less than 2 is less than 3, etc., and you take this to be the reverse order, so 1 is bigger than 2 is bigger than 3, etc., then this statement translates to this one. It says that whenever AWD and BWC are in the language, if A is less than B, then C is less than D, and vice versa. Okay, and I call this the symmetric order condition. And as I said, it's what you get if you replace this with the usual order and this with the opposite order, and that's what you get with symmetric interval exchanges. So then, what one can prove is that if you have a bi-infinite word X and its language, so this set of all factors of X, is closed under reversal, symmetric, I mean closed under reversal, like Arnoux-Rosie or Episturmian or symmetric interval exchanges, then X is singular if and only if L of X satisfies the symmetric order condition. So this condition here, which is fundamental to the orbit structure of symmetric interval exchanges, is more or less equivalent to the singular property. So using this, one can prove the following. So if I take a bi-infinite word, uniformly recurrent, bi-infinite word on the alphabet 1 through K, then the following are equivalent. X is singular and the language of X is symmetric, which this does not follow from that X is singular. And L of X is the language of a symmetric K-interval exchange transformation. So it's really the singular property that differentiates languages of symmetric K-interval exchange transformations from Episturmian languages or Arnoux-Rosie languages, okay? All right, so let's go back to finite singular words, because those are the ones we're interested relative to the sort of number theoretic extremal problems that we discussed earlier. So it turns out all Frankel words are singular, and they're also unique. They're the unique singular words in their abelian class, okay? Here's an example of a ternary singular word. It has 3 many A's, 5 many B's, 7 many C's. And also in this case, it's unique. And look what happens if I change the order of the parent vector. So still 3, 5, 7, but this time it's 3 many A's and so on and so forth. The word completely changes, okay? These are not word isomorphic, as you can see. And this is very important because the order counts here, right? When you're defining singular, the order counts. So here I'm assuming A is less than B less than C. And I'm assuming the same thing here. So the word really changes. So we prove that that it's always unique in the ternary case. So each abelian class over an ordered ternary alphabet contains a unique up to reversal singular word. That is, if X is given, in particular, if X is given by 3 distinct positive integers with their multiplicities n1, n2, and 3, then the maximizing arrangement for K dot is unique and independent of the values of the AI. So this confirms Ramharter's conjecture in the ternary case, okay? But uniqueness can happen also in other cases. So here's another example. Here I'm on 5 letters. And so I basically took the first word and I added a bunch of D's and E's. And so this is what it looks like. And it's also unique in its abelian class. So of all the, however many permutations this word has, this is the only one that is singular. Well, this and its reverse, okay? And remember the lemma that says that if you have a linear singular word and you add the symbol infinity, in this case I took it to be Z, and you close it up into a circle, then it becomes cyclic singular. So this is a cyclic singular word. And look what happens if I add a single D. So I kept everything constant. I just added 1 D, and you see the C's, which were nicely sort of all grouped together before, now get broken up into 2 groups. Okay, so as I said, we came up with an algorithm for constructing these words. This algorithm is based on a Euclidean algorithm coupled with a combinatorial algorithm. I will talk about the Euclidean algorithm, not the combinatorial one, because it's somewhat technical. But before I do that, let me just illustrate one sort of interesting last example. So here is a very simple example of 2 singular words that are abelian equivalent, but they're not reverses of one another. So they correspond to this paired vector. Okay, you can see they're not reverses of one another because there's just 1 A and both sides there. In both cases, they're in the same place. Okay, so this means that if A, B, C, and D were positive integers, then the maximum of K dot would either occur at X or at X prime. We don't know which one, because now for the first time, there's 2 possible places where the max can occur. So maybe there's some good reason that it should always occur at X, independent of the values of A, B, C, and D, or should always occur at X prime. So let's check it out. If I take the assignment A, B, C, D equals 3, 4, 5, 6, I find that K dot of X is bigger than K dot of X prime. So the maximum happens at X. Okay, let's try a different assignment. Let's take the assignment 3, 4, 7, 8. In this case, I find that the maximum occurs at both X and X prime. They're equal here. So this means that the maximizing arrangement is not always unique. So this is, if you want, the sort of a counterexample to what Ramharter had conjectured, that the maximizing arrangements should be unique and independent of the values of the positive integers. So here we see where it's not unique. And finally, with this assignment, it's X prime that beats X. The maximum this time occurs at X prime. So we see that the maximizing arrangement can depend, in this particular example, on the choice of the positive integers involved. Okay, so let me talk about the this non-commutative variant of the Euclidean algorithm. So first of all, let me explain what I mean by non-commutative. So you're familiar with many variants of the Euclidean algorithm. For example, the one that Milodi talked about that's associated with Arnoux-Rosie sequences, where you have, say, k real numbers, and you subtract from the largest the sum of the others. Okay, of course, you need the sum of the others is smaller than the largest. Okay, but in that algorithm, if you permute the columns, if you permute the entries of the vector, then nothing fundamental really changes. I mean, it's still true that the largest is bigger than the sum of the others. And when you run the algorithm, nothing really changes very much. And the same is true for other variants of the Euclidean algorithm where, for example, that are used to construct fine Wilf words on multiple periods. Here instead, we'll see that the algorithm is highly, highly dependent on the order in which you write these, this vector. And that's because of this quantity here, which is going to be key to the algorithm. So for each letter I, let delta I be the sum of the alpha j's for j bigger than I minus the sum of the alpha j's for j less than I. And you take this difference in absolute value. Okay, so you should be imagining that here alpha is either a paired vector of some finite cyclic word that you're trying to construct the singular word for, or it's the probability vector associated to a symmetric k-interval exchange. So this is the length of the first interval, the second interval, etc. Okay. All right, so having defined these delta I, so you can see here that the definition of delta I, it really matters who's to your left and who's to your right, okay? So having defined the delta I's, three possible scenarios can happen. The first case is all the delta I's are positive, okay? If all the delta I's are positive, then this breaks up into two subcases. The first one is that there exists a unique index J such that alpha j is strictly bigger than delta j, and for all other indices, alpha I is less than its corresponding delta I, okay? And if this was the probability vector of a symmetric k-interval exchange, and you always land in this case, then that's equivalent to being IDOC. The second condition is that there is a unique index j such that alpha j and alpha j plus 1 are equal to their respective deltas, okay? And for all other indices is strictly less than. So let me give you an example of what happens here in case B. Let's take k equals 5 and j equals 2. So we're saying that alpha 2 is equal to delta 2. So what is delta 2? Well, it's alpha 3 plus alpha 4 plus alpha 5 minus alpha 1. Normally an absolute value, but since it's equal to alpha 2, which is positive, this is equal to its absolute value, okay? So if you look at this condition, it's equivalent to saying that alpha 3 is equal to alpha 2 plus alpha 1 minus alpha 4 minus alpha 5, which basically says that alpha 3 equals delta 3. So we're really in this situation here, okay? And if I take the minus alpha 1 and bring it to the other side, this equation reads alpha 1 plus alpha 2 equals alpha 3 plus alpha 4 plus alpha 5. If I take this equation and I add alpha 1 plus alpha 2 to both sides, and of course I assume that this is normalized to 1, so when I add alpha 1 plus alpha 2 to the right, that's equal to 1. It's the sum of the alpha i's, the sum of the length of the unit interval. And on the left-hand side, I get twice alpha 1 plus alpha 2. Alpha 1 plus alpha 2 is the point we called gamma 2. It's the right endpoint of the second interval. So we're saying that gamma 2 equals 1/2. And that in turn tells you that the interval exchange will send gamma 3 to gamma 2, or inversely, gamma 3 equals T inverse of gamma 2. And this contradicts the D in IDOC. D is disjoint. Remember, the negative trajectories of the gamma i's should be disjoint. Well, here they're not. The negative trajectory of gamma 2 meets the negative trajectory of gamma 3. Okay, so in this case, the algorithm says subtract from the alpha j, whether we're in this case or that case, delta j. And then, of course, if you were dealing with interval exchanges, at this point, you would renormalize this so that it becomes 1. Now, notice that in case B, you get a 0 coordinate here, right? Because delta j is equal to alpha j. So you get a 0, which is almost like you've reduced the size of the interval exchange. And that's sort of what's happening here anyway. Let me just say that symbolically what this corresponds to, if you had an infinite word x that corresponded to the natural coding of this interval exchange with this length, and then what this corresponds to is you're actually deleting a j from each run of j's in the word x. And then you get a coding corresponding to this interval exchange. So I'll show that in a moment. Okay, so this is if these are the two cases that arise if each of the delta i's are positive. On the other hand, it can happen that some delta j is equal to 0. And in this case, j is unique. And geometrically, what this means is that the point 1/2, the midpoint of the unit interval, is the midpoint of one of the exchange intervals ij. So this, of course, means that the jth interval is fixed under the symmetric interval exchange, T. And so this contradicts the I in IDOC, right? It says that the negative trajectory of gamma j is finite, okay? If you ever land in this situation, it would say that the negative trajectory of gamma j is finite. So in this case, the algorithm just says, just delete the letter j. So you just, well, you subtract, you replace alpha j with a 0. And this represents the critical state of the algorithm. I mean, I sort of compare this to a paper jam in a photocopying machine. You know, you call the technician to have a closer look, because if you apply this algorithm to a Perec vector and you land in this situation here, this is exactly what can give rise to multiple cyclic singular words within the same abelian class. And that's what happened. If you remember the example, the simple example of a abelian class that had two non-equivalent singular words that corresponded to this Perec vector, which from a circular point of view corresponds to this one, where you add 1 for the symbol infinity. And notice the delta C is 0. C is this, so you have just as many letters bigger than C, namely 3, that you have less than C. On the other hand, if you can avoid this case, which let's say measure theoretically happens almost always, and so you're in this case here, then you either land in case 1a or 1b, then there exists a unique cyclic singular word having the prescribed Perec vector. So for example, if you run the algorithm with this Perec vector, you never land in this case 2, you always land in 1a or 1b. And so it means that relative to this Perec vector, there's only one singular word, and hence it's telling you that the maximizing arrangement for k dot, or the cyclic analog, is unique and independent of the values of the AIs. Okay, so let me end with just some conclusions. So the previous algorithm gives us a way of associating to each, let's say for simplicity, IDOC symmetric k-interval exchange transformation, an infinite directive word on the alphabet 1 through k, just as one does with episтерmian or Arnoux-Rosie sequences. Okay, and so one might ask, what is the symmetric 3-interval exchange transformation that has as its directive word ABC to the omega? In other words, the 3-yet analog of the Fibonacci word. Well, it's given by this interval exchange transformation T. So these are the interval lengths. If you apply the earlier algorithm to this vector alpha, you will always land in case 1a. And the index j that I mentioned before is going to alternate ABC, ABC, ABC. It's going to cycle through in that way. So more concretely, let x be the fixed point of this substitution on 3 letters. Okay. Then it turns out that x is the natural coding of the point beta 2. So this is the point of second point of discontinuity of the inverse of the interval exchange. Okay. Okay, so let me explain this last thing. So if you start with the fixed point x of this substitution, it's not difficult to see that you will have AA occurring as a factor. And that's because you have AC as a factor, and see that tau of A ends in A and tau of C begins in A. So you'll have AA. So take the fixed point x, and every time you see an A, or a run of A's, drop an A from that run. So in X, the runs of A's will be of length 1 and of length 2. But since you have one of length 2, the A's will survive this operation. Okay. But basically what you do is you just delete 1A from each run of A's. When you do that, the resulting word will have a BB. You can see that easily here. You see you have BAB. So if you delete the A, you're left with BB. So now you apply this operation, drop B. So you delete a B from each run of B's after, of course, you deleted the A's, okay? And now I claim the resulting word will have a CC. And you can see that because CA is a factor of X, and hence so is CABAC. Now, when you take CABAC and you delete the A's, you're left with CBC. And when you delete the B's, you're left with CC. So if you now drop a C from each run of C's, you get back X. Okay, so this is another way of seeing the ABC to the omega come up. In other words, X is of type A. It has AA occurring, but no other square of a letter. When you drop the A, then you see BBs. So the resulting word is of type B. When you drop a B from each run of Bs, you'll have CC, it'll be of type C, and when you drop the C, you're back to X and it starts all over again. The only thing I just wanted to mention is that this operation here is not based on episтерmian morphisms. When you have BB, it does not mean that B is a separating letter. Okay, so you're just dropping a B. It's not done in a morphic way. You can do it with transducers, but does not involve episтерmian morphisms. Okay, and that's it. Thank you very much.
Thanks, Luca. Does anyone have any questions?
Yes.
Yeah, Christoph.
Yes, thank you for this talk, very interesting talk.
Thank you.
I have a question and a comment. The question is, you said that the circular continued polynomial is maximized or minimized, I don't remember, by Christoffel words.
Yes.
I don't see that. This is the question. First, the comment is my comment is something else. Your algorithm, Euclidean, looks very like things which appear in the thesis of Mélodie Lapointe, because she constructed all tuples which are associated to discrete interval exchanges which have only one orbit. Her work itself is based on your paper with Ferenczi and in 2006, I think. So this was my question, my comment.
Okay, so with regards to the second point, that's very interesting. I would certainly be interested in seeing the thesis, as I'm not familiar with it. So let me try to go back to, with regards to your question. Let's see. I guess it's, whoops, did I pass it? Here. Yes, so what I'm saying is that if you take cyclic words on a binary alphabet, then singular is equivalent to being Christoffel. So that's something you just prove independent of other things. So the definition of singular is that whenever you factor X as U times V, then U is less than U star if and only if V is less than V star. That's the definition of singular for a cyclic word. And you show that that's equivalent to X being a power of a Christoffel word. Okay. Now, the consequence of that is that it means that in the abelian class of this cyclic word, so we're looking at permutations of cyclic words now, there's only one vertex without degree 0. And that's the one that you get by the Christoffel word. And that corresponds to the maximizing arrangement of the cyclic version of the singular continuant. In other words, if the letters in X are two positive integers, say 3 and 11, okay? So X is forget 11, say 3 and 7. So X consists of just 3s and 7s, and you look at it as a cyclic word. Of all permutations of this word, the one which maximizes this cyclic continuant is the Christoffel one. Well, or the power of the Christoffel if you take your definition of Christoffel to be primitive.
Yes. Is this published? Have you a paper or something?
No, it's not published. We're going to post, we're actually writing 2 papers. We're going to post the first in a couple of days. We're putting the finishing touches.
And who are your co-authors? I was not at the very beginning.
Alessandro De Luca.
Ah, yes, okay.
Yeah, and Marcia Edson, who is a former student of mine who now works at NSA.
Okay.
And yeah.
I have another. Yes, of course, you know that the value of the Christoffel word on this polynomial is the Markov number, yes. or 3 times the Markov number.
Mm-hmm.
So, of course, you You think to the Frobenius conjecture.
No, not really. I mean, I don't understand the relation because you're talking about regular continuants, and I'm talking here one of circular continuant and the semi-regular version. So this
It's
is
a semi-regular here.
Yeah, this is semi-regular. It has a dot and it's
Okay.
cyclic.
Okay, I see. No, because
Yeah.
if you remove the dot, you obtain the Markov number. I mean,
So
3
you have to
times.
maybe you have to remove the circle too.
No. It's a property of.
Cyclic words. I see. Okay.
Yes.
Okay.
Okay.
Yeah, so it would be interesting to understand the connection between the two because these regular and semi-regular continuants are quite different.
Yes, of course.
And I think in one case without the dot, there's actually a minimum going on. It's a minimizing thing, and here it's maximizing.
Mm-hmm.
I think Dominique had a question.
Yes. Do you hear me?
Yes, I hear you.
Okay. Hello, how are you?
Fine, thank you. How are you?
Yes, thank you for this wonderful conference. I have a question. The last thing you said about the directive sequence for the interval exchange transformation, does it mean that you have a characterization of the natural representation of IETs by their S-adic representation?
No, I didn't. I don't think I said that.
No, but
yeah.
You didn't say that. But I'm just putting this one step further.
Yeah. Okay. So I vaguely thought about that question, and I haven't thought at length about it, but there might be something interesting happening because in the case of what I had said here is that if you apply this algorithm to a paired vector, so forget interval exchanges for a moment, and you ever land in the case where the delta J equals 0, okay, then I get the impression that, at least in our combinatorial algorithm, it's very far from being morphic, this process. And so I'm wondering if, when you're dealing with interval exchanges, if you land in a situation where the delta J equals 0, if this can be done morphically or not. In the other cases, you can. In the two cases here, this can be done morphically, although the second case is not letter to letter. The first one is just episтерmian morphisms. This is well understood. This one, you need a transducer. You need to look at factors of length 2. But in this case, at least for paired vectors, something really strange happens. It's like I said, it's like a paper jam in a copier. And as far as I can tell, this cannot be done morphically. But I haven't looked at it in the context of interval exchanges, just in the context of paired vectors, so where the alpha i's are positive integers. So I don't think I've answered your question, but I've wondered about that. And I think that in this critical case, there may be a possibility that something not morphic is happening. I don't know.
All right, thank you very much. Jeff's got a question.
Yeah, more of a comment than a question, if it's okay. So you talked about how intricate the structure of these min achieving and max achieving words are in general. And I think that the reason for this is basically that the associated decision problem in general is NP complete, and even more than that, is not even approximable within a constant factor unless P equals NP. And there's a nice paper by Ann Condon in the early 90s where she shows that, if you have a bunch of matrices and you want to know, is there some product of n of them that is greater than some bound B, then that decision problem is NP complete. So
okay, yeah, no, I'm also not familiar with that.
So that suggests why, in general, Of course, it doesn't apply to your specific case because it's a general thing, but in
Uh-huh.
general, it will be really hard to understand the structure of these things.
Yeah, except that what you see is that in 3 of the 4 cases, the structure is fairly well understood. These words are very regular. It's just the 4th case, which is very elusive.
Right.
And then, of course, I
but
mean, we
that's-
have an algorithm for constructing them. So now we understand how to build them. But when we first started looking at them, it was like Chinese to us. You know, I mean,
Yeah.
we couldn't understand where these words were coming from. They were very far from looking very regular, like palindromes or anything like that. And now we understand them a little bit better. But certainly there's this one case that behaves very differently than the other 3.
All right, we've gone a bit long, so maybe we can wrap things up. So thank you again to Luca.
Thank you very much.
For this talk. Before we go, I just